Hello, I am Patrick from Sumitech Turbomachinery Solutions. The objectives of this presentation are to familiarize rotating machinery engineers involved in detailed engineering and site operation. Sensor mounting, methods of proper setting of thrust bearing end play and voting are also discussed as a part of on-site work carried out during pre-commissioning activity of mission-critical turbomachinery. The first part had explained types of thrust bearings. The second part shall explain thrust positioning of rotor, installations and setting alarm and trip. Thrust bearing damages can occur within an extremely short time and with little warning. Monitoring of the axial thrust position allows the early detection of damages and failures of the thrust bearings, which could lead to the destruction of the machine. Normally, we use redundant relative shaft displacement sensors when hydrodynamic thrust bearings are used. Axial thrust monitoring in multistage pumps/compressors is vital for preventing bearing failure, using methods like thrust balance devices, drums, discs, balance holes, back-to-back impeller arrangements, to counteract immense hydraulic forces, monitored through shaft position sensors, proximity probes, and vibration analysis to detect imbalances from design changes, fouling, or operational upsets, ensuring reliability by comparing actual thrust loads to predicted loads. In a steam turbine, axial shift refers to the movement of the rotor along the horizontal axial axis. While small axial movements are natural due to pressure differentials, excessive axial shift is dangerous and can lead to catastrophic failures. Axial shift is controlled. 1. Thrust bearings. Located at one end of the turbine shaft. Absorb axial loads and limit shaft movement. Tilting pad thrust bearings are commonly used. 2. Axial shift detector/positioning probe. Uses eddy current sensors or LVDTs to measure shaft displacement. Monitors real-time axial movement. 3. Alarms and trips. Control system generates alarm at preset deviation. In large turbomachinery, the thrust bearing assembly is usually located either inside the front standard or between the HP/IP turbine and the first of the LP turbines, and it is intended to control the axial movement of the rotating shaft relative to the stationary case, as it warms up during startup periods. In this arrangement, the front standard is usually permitted to move axially to accommodate the thermal expansion in the other direction from the HP/IP turbine sections, but it is restrained from moving radially. Depending on the physical layout of the machine and the location of any critical areas, sensors may be installed between the front standard and the foundation, or between the front standard and the HP/IP casing. For case expansion, these are usually linear variable differential transformers, LVDT, which provide greater linear range than an eddy probe and can accommodate the expected greater expansion values at these locations. The LVDTs are usually configured with a spring-loaded plunger and are installed with the plunger ball bearing tip riding against the moving case, ideally on a machined flat surface which is perpendicular to the main axis of the rotor. Temperature fluctuations cause differential expansion in machines, which alters axial clearances and alignments of internal components. Differential expansion is the disparity between rotor and casing expansion. Positive, plus VE, if rotor expands more than the casing. Negative, VE, if the casing expands more. Calculating differential expansion rates helps identify these variations to protect against axial rubs between rotating and stationary components. If the differential expansion gets too severe, it can lead to a failure which results in either expensive repairs or entire machine replacement. The rotor position is fixed at the thrust bearing to restrict its axial movement within the turbine casing. This means the rotor will thermally grow away from the thrust collar and contract towards thrust collar during differential expansion. This is important to remember when setting rotors and determining startup and shutdown time periods. The important transient issues on high-pressure, high-temperature steam turbines, especially with uneven side and up growths, requiring operators to monitor the loose washers at main pedestals, which must remain loose. If not, there will be problems during beginning the equipment run. That's why we need to increase RPM slowly, with carrying thermal expansion of turbines casing by watching movement of mounting feet. The rotor of a machine is physically held in place by the thrust bearing, but depending on where the fixed or pinpoint is located on the machine, the thrust bearing can also slide as the machine expands. In any case, as the machine heats up or cools down, it is vital that the rotor and the casing grow at the same rate so as to avoid rotor-to-stator contact, which will invariably destroy the machine. Therefore, during transient phases of operation, startup or cool down, heat-soaking indwells are used to ensure that thermal expansion or contraction to not cause rotor-to-stator contact. It is common to use non-contact probes, eddy current probes, attached to the turbine casing to observe the rotor, thereby measuring the difference between the movement of the rotor and the casing as they thermally expand, to measure the differential expansion. Ideally, the two probes are mounted onto the same dual probe carriage as shown above, but other arrangements can be accommodated in the system configuration, but are more complex to set up. The red line indicates the transmission of net axial forces from the high-speed pinions to the low-speed bull gear shaft through the thrust collars and rider ring. Few slides shall show few assembly and dismantling process. During annual turnaround if required, check the condition of thrust bearing pads for scratches or signs of other damage types on thrust collar. These picture some at-site activities and checks. These pictures show various stages of installation of thrust bearings. Sometimes rotor has to be shifted to one extreme position using a crowbar. Extreme precaution to be exercised. Determine total rotor float. Using a hydraulic jack or other constant force mechanism, push the rotor to its extreme positions against both the active, working, and inactive, non-working, thrust bearing pads. Use a dial indicator to measure the total axial travel, float of the shaft. Repeat this process to verify the repeatability of the readings. Position the rotor at the reference point. The most common and recommended practice is to position the rotor at the mechanical center of its total float, mid-float. This provides symmetric measurement range for movement in either direction. Alternatively, some procedures call for positioning the rotor against one specific bearing, e.g. the outboard bearing, and designating that as the 0 point. Keep dial indicator at measuring point. Apply a suitable axial load, not a jerk, once towards active side and next on inactive side. Check mechanical float. Check gap voltage and repeat several times. Mount the proximity probes so their axis is parallel to the shaft axis. Position the tip of each probe at a specific distance from the target surface, typically around 0.050 inches, depending on the probe's linear range. This distance is adjusted to achieve a specific gap voltage, e.g., -10 VDC, in the linear range of the probe driver. If the shaft end is countersunk, the probe should be mounted off-center, ensuring the tip is at least 1.5 times its diameter away from the edge. With the active thrust shoes on the inboard side of the bearing, and normal thrust load acting away from the probe mounted on the end of the shaft, it is easy to define axial movement directions. Specifically, increasing probe gap voltage is indicative of normal thrust position on the active shoes. Conversely, a decreasing gap voltage is indicative of counter-thrust motion towards the inactive thrust shoes. Identify normal thrust direction and thrust bearing configuration and probe location. Check thrust bearing float. Set gap voltage repeat check by turning shaft 2 times by 180 degrees for repeatability. This activity ensures that thrust collar is 90 degrees orthogonal to shaft center. Thrust position measurement is based upon a linear relationship between the proximeter output voltage and the average distance between the probe tip and the observed surface. The slope of the calibration curve is the transducer system sensitivity in units of millivolts/mil or micrometer. The industry standard is 200 mV/mil, 7.87 mV/m, with a plus or minus 5% tolerance. This is equivalent to a range of 190 to 210 mV/mil. The linear range is typically required to be a minimum of 80 mils. It is useful to note that the inverse sensitivity is 5 mils per volt, equals 1/0.2. Specifically, every 5 mil change in probe gap should produce a 1.0 volt change in DC voltage. This makes it convenient to evaluate the linearity of a calibration curve during acquisition of the calibration data. A calibration curve is plotted for the eddy current sensor and its related readout device. This calibration curve will be for the metal of the shaft to be sensed, and the plot will be volts, ordinate versus gap, abscissa. Gap implies the space between the probe, eddy current sensor face, and the metal used in calibration. Setting of thrust probe voltage ideally, The center of the transducer's linear range should correspond to the center of the rotor's float zone, but it is difficult to position rotor in the middle of the float, so we set the rotor to one end of the float and set the voltage correspondingly. In this case, center of linear range is 10.0 V. Float is 16 mils, half of which is 8 mils. If rotor moves to one side, voltage will increase or decrease by 8x 200 mV/mil equals 1.6 V, so when rotor is in active side, set voltage to 10 plus 1.6 equals 11.6 V. Hot float zone will be more than the float measured in cold with plus or minus 8 mils float. The hot float will be around +/-12 mils. Set alarm, so that some babbitt will be removed before alarm actuates. About 6 mils beyond hot float, or about plus or minus 18 mils danger or trip, may be set 10 mils beyond alert, or at +/-28 mils. API 670, American Petroleum Institute, specifies dual voting thrust position at each thrust bearing. This approach to thrust position measurement requires that two transducers be mounted at each thrust bearing. Their respective output signals are then compared to alarm and shutdown limits. Both output signals must exceed the shutdown limit before the machine is tripped. This method of thrust measurement increases the system's reliability and is recommended for shutdown operation in most applications. Two thrust probes are installed to provide redundant measurements. This is mandatory for systems that are armed for automatic thrust position shutdown. In these applications, both thrust probes are connected to a common thrust position monitor, and various schemes of voting logic are used to trip the machine. Some users require both thrust probes to indicate trip, and others include thrust bearing temperature into the trip ladder. Obviously, multiple schemes are possible, and the end user should standardize on trip logic for the critical process machinery. Directional clarity. Ensure that the monitoring system and operators clearly understand which direction of voltage change corresponds to movement towards the active or inactive thrust shoes to aid in troubleshooting. Thrust bearing temperature. Axial position monitoring should always be supplemented by thrust-bearing metal temperature measurements, as pad wear is a critical failure indicator. During first installation and after every turndown inspection, this sheet is populated and to be kept as record in files, and soft copy must be with reliability department. If thrust bearing is subject to critically high loads, continual thrust measurement will give you a vital indication of machine and bearing condition. To measure thrust, we can install a strain gauge load cell in one or more of the upper leveling plates or thrust shoe. This load cell is simply a steel column which is stressed in compression under load. Wire-resistant strain gauges mounted on the column register the strain. Since the strain is directly proportional to load, instrument readout can be calibrated to show thrust directly. This slide shows a typical case study where, even with absolutely correct design of compressor, had caused repeated damages of thrust collars of pinion shaft and bull gear rings. If you watch carefully on top left of this slide, you can see the intricate taper profile of thrust collar, just like the profile of taper land thrust bearing. However, in this case, the tapers were at reverse direction, which caused the lube oil film breakdown as the machine attained higher speed, which caused severe damage to pinion and bull gear thrust collar and ring. So, the importance of correct profile is as sensitive to a thrust pads of bearings. If both probes looking at end of shaft, there are few points to ponder. Advantage: will always detect changes in axial position of rotor. If connected to trip, will always prevent rotor stator rub. Disadvantage: will not directly detect looseness of thrust collar. However, looseness of thrust collar can be inferred indirectly from the fact that bearing temperature will not go up even when thrust position reaches alert level. Some plants have tried to vote thrust position with bearing temperature through an external and gate, thinking this would further improve reliability. Seems logical, but can be dangerous under following circumstances. There are several situations when real high axial position may not be accompanied by high bearing temperature. Loose thrust collar. Axial load would not be transferred to thrust bearing. Bearing temperature would never increase electrostatic discharge damage. As babbitt is slowly eroded, shaft would move axially, but temperature would not increase much. Sumitec Turbomachinery Solutions is your trusted partner for all your turbomachinery needs. With our deep expertise, innovative solutions, and unwavering commitment to excellence, we empower engineers and organizations to achieve peak performance and reliability in their critical rotating systems. Let us guide you through the complexities of the turbomachinery industry and help you unlock the full potential of your equipment.